This module on securing the SD-WAN control and data planes explains how the control and data planes are encrypted in VersaSecure SD-WAN and the key processes used for secure communication between devices. At the end of this module, you will be able to explain how the control and data planes are isolated and secured in SD-WAN and define the key security protocols used for data encryption. Enterprises contain information that is both private and public, and it is the duty of the enterprise to protect the private information, be it the intellectual property of the enterprise, the financials of the enterprise, customer subscription information, payment information, or other information that has to be safeguarded due to standard and federal regulations. VersaSecure SD-WAN provides secure segmentation and isolation in the control and data planes to protect enterprise data and security. Let's discuss how the control and data planes are separated in the VersaSecure SD-WAN solution. In the example in the image, when branch 1 comes up, it establishes an encrypted tunnel, or a pseudo-tunnel virtual interface, or PTVI, connection or control plane tunnel with the control VR located in the Versa controller. This tunnel is essentially a secure VPN connection to the Versa controller. After establishing this PTVI connection, the branch receives information on how to establish a VPN connection to branch 2 through a secure multi-protocol BGP session to the controller. And based on this information, the data plane VPN connection to branch 2 is established. This dynamic tunnel is called a DTVI, or Dynamic Tunnel Virtual Interface. This too is a VPN connection. The control and data planes are segmented and isolated. When multiple tenants coexist in the same device, the same process will occur, with separate VPN tunnels, or PTVI and DTVI connections, for each tenant. Once the first control plane tunnel is established and a secure BGP session is established between the edge device and the Versa controller, multiple dynamic data tunnels are created to connect discovered sites. Let's look at the control and data plane separation in more detail. To enable a graceful transition from one WAN circuit to another, VOS implements a layer of abstraction between the tunnel interfaces and the actual physical interface over which tunneled data is sent. A DTVI in a control VR points to an indirect internal next hop to forward traffic. That indirect hop directs the traffic towards the designated WAN exit interface within the WAN interface's transport VR. The tunnel encapsulation does not use the tunnel endpoint address as the source or destination address of the packet. Instead, the VPN tunnel interface combination is used to encrypt the data and to associate it with a transport path. The original source IP address and destination IP address of the customer traffic remains as the inner source and destination addresses, and the outer header uses the source and destination addresses of the transport network path referred to in the indirect next hop during packet processing. Once the data arrives at the remote site, information in the encapsulation header, such as the circuit information in the VXLAN header and the MPLS site label, identify to which local tenant the traffic should be forwarded after decapsulation. In the event that the transport path needs to be changed during a session, only the forwarding next hop of the outer header is changed to redirect the traffic over the new path, and the underlying application session is unaffected, making the transition seamless to the end-user application. Versa SD-WAN uses Information Key Exchange, or IKE, which is a security protocol to implement secure association and communication between two or more devices. It offers common peer authentication by utilizing shared key or cryptographic keys, while also protecting the identity of the device. IKE uses Diffie-Hellman exchange for generating the shared secret key. Diffie-Hellman key exchange is a method used to establish a shared secret key while exchanging information over a public channel. As shown in the image, this method uses a combination of a private key and an equivalent public key to generate the shared secret. The IKE process is used to establish secure tunnels between CPE devices and the Versa controllers. For encryption between CPE devices, Diffie-Hellman key exchange is used, But the IKE process is not used for this key negotiation. Branch-to-branch Diffie-Hellman key exchange is performed through the secure multi-protocol BGP updates between devices, and every pair of devices has a unique key pair. If a branch device creates tunnels to multiple remote sites, each remote site tunnel will have a unique encryption key pair, and therefore unique encryption. The outer encapsulation and transport used to forward the tunnel traffic can be based on various factors such as routing information, policy, and SLA parameters. The indirect next hop functionality allows any one of many different policy-based forwarding processes to redirect traffic towards a transport network dynamically. The outer header is based on the outbound interface and transport network parameters, which is used to send data across the service provider. The virtual interfaces can be viewed through the CLI on the device. Click each highlighted section to view its description. You have reached the end of this module. In this module, you learned that Sercuring SD WAN provides secure segmentation and isolation in the control and data plane to protect enterprise data and security. SD WAN uses Information Key Exchange, or IKE, which is a security protocol to implement secure association and communication between two or more devices. Diffie-Hellman key exchange is also used to establish a shared secret key while exchanging information over a public channel. And every site-to-site VPN tunnel has a unique encryption key pair, and therefore has unique encryption.